Welcome back. We are in circular motion universal gravitational unit here on the worksheet 3, the universal gravitational problems here. So we have number 9 here. I'm going to go do number 9 here for you. The planet Mars has some mass there, a bunch of mass, completes an orbit around the sun in 687 days. The sun has this mass here. What's the average radius of the orbit of Mars? Interesting. Let's go draw a picture. I always start with a picture here because I get really confused. If you're saying to yourself, I don't know how to solve this, hey, don't worry. I'm in the same boat every time that I do stuff like this, even though I've done this before. I read a problem like this, and I, most often, including right now, I say to myself, yeah, I'm not entirely sure how to actually go and solve this. But I know that if I get some general idea of what's going on in this problem here, and I follow all of the things that I know work in all of these other problems, I bet I'm going to make some progress. And I bet you will too. So let's go do that. So what's going on here? Well, I know that Mars is going to get a force of gravity on Mars by the sun there. Absolutely. And what else do I know? Well, I absolutely know that Mars is pulling on the sun there, and it's pulling just as hard, right? This force is the same as that force by Newton's third law, as well as just the universal gravitational equation. We can put that in there and see that it'll be the exact same as well. What are we trying to find? We're trying to find the radius. Now, the radius is the radius between the center of mass of one object and the center of mass of the other. Again, the center of mass is outside of this scope of this course here, but we're just thinking to the geometric center of each of them, which is actually a pretty good approximation, especially in this case here. Okay, so we're looking for that radius there. Well, what am I going to do? Well, I'm going to make one of these things my system here, and I'm going to sum up the forces here and see, what's going on here. So which thing I'm going to make my system? It doesn't matter. I'm going to make Mars my system here. So I'm going to make Mars my system here, and I'm going to see that, well, it's going in a circle here, so I should probably use the tangential and radial dimensions here. So that's the negative radial dimension. That's the positive radial dimension over there. And so let's go do that. I'll do that in blue here because why not? We'll sum these forces up in the radial dimension. And there's only one L in radial, as always. So sum them up. It's equal to m times a. What do we got here? Well, I know that I have the force of gravity that's going inwards there, so that force of gravity is positive there. Cool, great. That's equal to m times a. Now, what do I know? I don't know the force of gravity, but I do know the big equation for the force of gravity. Maybe that'll be helpful. Let's go ahead and let's put that in. So big G m1 m2 over r squared. Now, which one's m1 and which one's m2? It doesn't matter. I'm going to go ahead and label the mass as the sun as m1 and the mass of Mars is m2. Or actually, probably what makes more sense is instead of writing m1 and m2, maybe I'll just write ms for the sun and mm for Mars there, divided by the radius squared. Boom. That's actually even simpler because now I don't even need to actually define those, and I think most people can follow along in this problem here. Now, on the right-hand side, let's see what we can do on the right-hand side. I have mass times acceleration. Now, careful. What mass do I have here? Think about it. I'm summing up the forces on what object? I chose my system to be Mars here. So this mass over here is always the mass of my system, and I chose it to be Mars. I could have done it for the sun there. I just chose Mars in this case. Okay, cool. So I know that this mass here has to be the mass of Mars. That's very important. It's dependent on what system you've made there. And if you don't know what system you've made there, it's easy to get mixed up there. Now, it's equal to, or it's this mass times the acceleration here. What's the acceleration? Well, it's going in a circle here, and we're going to average it, or we're going to approximate it to a perfect circle here. The actual orbit of Mars is pretty close to a perfect circle. It's only 9% off from a perfect circle around the sun. So anyways, so then I'm going to go ahead and I'm going to substitute in the tangential velocity squared divided by my radius there for the acceleration, as we've done this many times before. And so I know that this is a centripetal acceleration, and so then it's equal to my tangential velocity squared over the radius. Okay, cool. Now, how is that helpful? Well, notice that I'm trying to find the radius here. So R is a big question mark, and check this out. I have R in my equation here. I know these masses, I know this G, I know this mass. Do I know the tangential velocity? No, it doesn't tell me that. But wait, hold on a second. It does tell me some information about how it goes around the sun there. Hey, it takes that many days to go around the sun. That's a period there. That is a time value, right? That is defined as a period because it's going around and starting to repeat some motion there. So that's the time that it takes to repeat some motion. In this case, it's 687 days. 687 days for one revolution. Okay. Now it's just 687 days per one thing that it's doing. In this case, it's a revolution because Mars is revolving around an external point that it's rotating. So it's rotating basically around somewhere around the center of the sun. It's just a little bit off because it's actually the center of mass between both of those objects, which is like a little bit closer to Mars. So it's somewhere over here. And so the sun is actually wobbling around as Mars is going and orbiting around this. You don't have to worry about any of that. Anyways, the point here is that Mars is revolving around a fixed point outside of the body of Mars, and that's why we call it a revolution and not a rotation. Mars, actually, I don't know if Mars is rotating or not, but the Earth is rotating. Earth rotates, and we call it a rotation, and that's where we get our days from, because it's rotating around, the north and south pole, you might say. It's not actually, but it's somewhere around there anyways. And I believe Mars does rotate. Yes, it does rotate. I think about other things now, and it does. Anyways, we look at the time value here, the period here, and go, wait, I know that if I have the period, sometimes I can figure out the velocity. But check that out. That's 687 days. That's not SI units, so let's get that into seconds there. So it's 687 days per one revolution. And so now I need to get that into seconds there. So I know that there's 24 hours in one day. And then I know that there's 60 minutes in 1 hour. And I know that there's 60 seconds in 1 minute. And I look at that and I go, oh, that's right. Yeah, all of those units there cancel out with one another. And I'm left with just seconds. So I can go and I can pick up my calculator and figure out what that is at some point. Well, I guess I'll just go do that right now. I pretty much always, and I recommend it for you as well, anytime that I see some unit that is not SI units, I change it right away because I'm probably going to forget later and I don't want to forget. That would be a silly thing. I don't want to do all of this work and then mess up because I forgot to convert something. That's like the easiest thing that I could possibly have done. And so I get this big value there. I'm going to store, that's a big number there. So I'm going to store that as T so I don't have to type that in later. But I will write it out here for you. 59356 593, I already forgot it. Dang it. No, I didn't. Okay, 56800. 56800 seconds. Right, that's the period there. How is that helpful? Well, I'm checking out, I'm looking at this tangential velocity here. So I'm looking at the tangential velocity going, hey, it's going around a circle there. So that's the distance of 2 pi r. And it does that in a period there, which is this big number there. And so I can go and I can substitute this in for my tangential velocity. Notice it's tangential velocity squared, so don't forget, I got to go and square that thing. So I'm going to take this and I'm going to put it in for right in there. And so that's how my period is going to help me. So let's go copy all this stuff down again. I got big G, the mass of the sun, the mass of Mars, divided by my radius squared. That's equal to the mass of Mars. And now I put in this thing here. So I got 4 pi squared. Don't forget to square the pi. That's usually what I forget to square myself. Radius squared divided by t squared. And then I have my radius there, and that's in the denominator as well. So I'm going to skip that step there, but I'm just doing that slight algebra of going, the t squared just goes right into the denominator with that r there. So this r is that r right there, even though it looks all funky because I messed up writing it. Okay, there we go. Okay, so if you're with me there, now we can let's go clean this up because it looks like I have everything. I know G, I know these masses. I don't know the radius, but that's what I'm trying to find. I know this mass, I know these guys. I don't know that, but that's what I'm trying to find. I know t, and that's what I'm trying to find there as well. It looks like I can go and solve this. So let's do some algebra and clean it up. First, I see that I have these masses of Mars in common here, which means that they cancel out, which means the mass of the orbiting planet doesn't matter. Wow, that's interesting. I look inside here and I go, hey, one of these radius, one of those radii cancels out with the other. That's nice. I need to get the radius by itself there, so I'm going to move this radius here to the other side because that I just multiply by r squared, and then I get it into the numerator there, and I need to have it in the numerator so I can actually solve for that. So that's what I'm going to do in the next step here. I'm going to move the 4 pi squared over to the other side. Let me do that step by step, and so I'll just talk it out here. So I'm going to move this 4 pi squared. I'm going to divide it to the other side there, 4 pi squared. I'm going to move the r squared from the denominator and multiply by both sides and get r squared times r over here. And so that'll give me r to the third power. Again, I move that r squared to the numerator over here by multiplying by r squared, but that's r to the first. So r to the first times r squared gives me r to the third. Now I still have t squared in the denominator here. I'm going to multiply both sides by t squared so I can get that away from the right-hand side. And so then that t squared is going to be in the numerator. Now I just go back and I double check. Do I have everything? I got G, got MS. I have my R squared and R cubed, 4 pi squared, got that there. And the pi is squared. I always forget that. And then T squared, I do have that there. Looks like I have everything that didn't cancel out here. Well, I need to get R, not R cubed here. So I take R and I'm going to take the cube root of everything on the right-hand side, not including the equal sign, which it kind of looks like there. And so I got big G, the mass of the sun, t squared divided by 4 pi squared. I could go and write in all of those values if you care to, or you could just put it straight in your calculator. It's usually what I do, 6.67 times 10 to the negative 11 for that G. Mass of the sun, it told me 1.99, 10 to the 30th. Man, it's so big. 1.99, that's multiplication times 10 to the 30th kilograms. That t squared there, it's 593,56800. 593,56800 squared. And then divided by 4 pi squared. I'll leave that for the calculator there. So let's go grab our calculator and put all of this in. Now, I have already programmed in what G is. You should too, because it just simplifies things. Don't make things harder for yourself. I'm going to go to math and I'm going to go down to number 4 there and get the cube root. Do G times the mass of the sun there, 1.99 e to the 30th power. Remember that e means times 10 to whatever power. It automatically puts that scientific notation in parentheses. The multiplication between G and anything next to it is implied that it is multiplication. Multiplied by t squared. So I already, as you saw, I already stored t as t. So and then that makes it way easier to type in, doesn't it? And then I go and divide that by, and I put that in parentheses there, so it actually keeps those bits in the denominator there. And that is necessary for those parentheses there. And then that's it. So press enter. So here's the radius, 2.28 times 10 to the 11th. 2.28 times 10 to the 11th meters. I know that it's in meters because I have only SI units here, and the SI units for some radius or distance would be meters there as well. I could go and look and make sure that that matches up. Hey, it does match up. Now notice that my honest assessment at the beginning is I don't know how to do this. Well, yours might have been too, but notice, draw a picture, label things that you know. I got some forces going on there and some radius, and drop a coordinate plane. Some of the forces, and just start substituting things in as you have available that might help out. Sometimes you get stuck, and that's okay. You can go back and restart. But boom, you just do some algebra and you get there. Boom, not too bad. All right, have a beautiful day. See ya.